All right, thanks for coming this morning. Ken Caldera is a scientist at the Carnegie Institution Department of Global Ecology and a professor by courtesy at the Stanford University Department of Environmental and Earth System Sciences. Previously, he worked for 12 years in the Energy Environment Directorate at the Lawrence Livermore National Lab. And his diverse research interests include numerical simulation of Earth's climate, carbon, and biogeochemistry, ocean acidification, climate emergency response systems, evaluating approaches to supplying environmentally friendly energy services, ocean carbon sequestration, and long-term evolution of climate and geochemical cycles. Ken has a BA in philosophy from Rutgers College and an MS and PhD in atmospheric sciences from NYU. So without further ado, Ken, thanks.
Thank you, Kevin. So today I'm going to speak about geoengineering Earth's climate. And I'll explain what I mean by that in just a second. But an alternate title and perhaps the topic of my talk is this question of, is it time to start working on a climate emergency response system? That we hear a lot about the threat that there might be some kind of climate catastrophe or climate emergency where that's poorly defined, and different people have their own ideas of what would constitute an emergency. But I would just suggest that it's time for us to start thinking about what we would do if something goes seriously wrong with our climate system. One of the things that leads me to be interested in this kind of work is the record of our carbon dioxide emissions. And what you see on this figure is a number of the major IPCC carbon dioxide emission scenarios developed in the 1990s, overlain with two estimates of actual carbon dioxide emissions. And what we see is that carbon dioxide emissions today are at or above the emission rates foreseen in the most pessimistic of the IPCC scenarios, and that over the past few years, CO2 emissions have been rising much more rapidly than in any of these scenarios. And there are several reasons why this is happening. One is the high price of oil is pushing people towards coal, which is much more carbon emission per unit energy derived. And then also the rapid development of China and India and other countries are making CO2 emissions rise very rapidly. The subject of this talk is not the scale of the effort needed to transform our energy system, but suffice to say that it's truly a Herculean task, which we could do if we set about doing it as a society, but at least as indicated by carbon dioxide emissions, so far that we've done essentially nothing effective to reverse the increasing CO2 content. Also, as we know that sea ice is disappearing rapidly, a number of other indicators that climate is changing very rapidly are presenting themselves. And so while it would be nice if we would reduce and eliminate carbon dioxide emissions as soon as possible, that we don't seem to be doing this, and so we might think about, well, what do we do if our efforts to reduce carbon dioxide emissions don't avoid dangerous interference with the climate system? So, I've been in this business long enough that I remember when people used to show maps of what kinds of temperature changes might occur from a doubling of atmospheric carbon dioxide content. And people used to present these figures as, oh, this is how bad things could be if we don't wise up soon. And really, we've gotten to the point where we're showing these kind of maps and saying, well, this is how good things could be if we work really hard to transform our energy system. Because to get much below a doubling of CO2 would really, we can do it, but we really would need to more or less stop making carbon dioxide emitting devices as soon as possible. So, what are the strategies to stabilize climate, or at least, to stabilize climate? And we could think of four major categories. One is to diminish end-use energy demand, and that basically means either improving efficiency or having sectoral shifts so that we sort of use, start using books instead of riding four-wheel drives through the deserts or something, or just conserve and do with less. The next major category is to produce energy without carbon dioxide emission. This could be renewable energy sources or perhaps nuclear sources. And then there's the idea of actively removing carbon dioxide and other gases from the atmosphere. But these three methods all affect the amount of heat radiation that escapes from the Earth's surface to space. And an alternate approach is to reduce the amount of sunlight absorbed by the Earth. And the basic idea is that the Earth is heated by the sun, and then it cools off by radiating that energy to space as long-wave heat radiation. And so if the Earth is having more difficulty radiating out to space, well, one way to compensate that is to reduce the amount of sunlight that the Earth absorbs. And so in the context of this talk, other people have different definitions. I'm going to use geoengineering to refer to the intentional large-scale manipulation of Earth's radiation balance. And more particularly, I'm going to focus on the intentional large-scale effort to reduce the absorption of sunlight by the Earth. And so there are a few different schemes that have been proposed. Here's a little picture of the sun and the Earth revolving around the sun. And there's a mark there marked as L1 over here. It's marked by the X. And that's a point at which the gravitational forces of the sun and the Earth are balanced when you also take into account the apparent centrifugal forces and so on. So something placed at this L1 point is neither pulled towards the sun nor the Earth, although it's an unstable unstable steady state, so you would need some controls to keep things there, but it wouldn't take large amounts of energy. So one idea is to basically block the sun by putting satellites or reflectors or deflectors 1 million miles out in space between the Earth and the sun. What I think is a more practical idea is that putting particles in the stratosphere to deflect sunlight back to space. And people have also suggested putting whitening clouds over the ocean. And then, well, it might not fit with the large-scale idea. The idea is you could also lighten the Earth's surface by, say, making roofs wider or making roads wider. And all these things would help to cool the Earth. But what's the scale of what we're talking about? That each doubling of CO2 in the atmosphere, so if you take the amount of carbon dioxide in the atmosphere and you double that, that prevents about, instantaneously prevents about 2 times 10 to the 15th watts of energy from escaping to space. Now, just for comparison, right now, we're using more or less, the human civilization is using something like 15 times 10 to the 12th watts. So if we call that 2 times 10 to the 12th watts, it's something, the amount of energy used by a civilization is less than 1/1000th of what the amount of energy trapped by a doubling of CO2 content in the atmosphere. In contrast, the Earth is absorbing over 10 to the 17th watts at any given time. And so if we just divide these two numbers, we'd say that if we wanted to have the Earth absorb roughly 2 times 10 to the 15th watts less energy, we would need to deflect about 1.7% of the sunlight coming into the Earth. And okay, and so now that the Earth happens to be a big place, and so if you said that we're going to do this in the stratosphere, and so then you need to block 1.7% of the whole spherical area of the Earth. This ends up being 8.5 million square kilometers. So you could think of this as, if this was a patch 1,000 by 1,000 kilometers on the side, you need to block 8.5 of those, which is pretty big. Now, because with the geometry of the Earth, if you had to put something between the Earth and the sun, you just need to block the disk area, not the whole spherical area of the Earth. And so now we're talking about 2 million square kilometers. Still rather large structure if you're going to build a structure like that out in space. So, I mean, my basic point is I think this idea of building this out in space is not really practical. And whereas I think this one is eminently doable. One of, just to be a little disorganized in this talk, the geoengineering has been proposed to play at least two kinds of roles. One is sort of as somehow a replacement for CO2 emissions reduction. And the idea is that, if we want to limit ourselves to some amount of warming, that we can continue emitting more CO2, and then you try to geoengineer the planet to reverse that. And another view is what I'm presenting this as is some kind of emergency response system that if something really catastrophic happens, that you'd take these desperate measures. And this idea of building something out in space of this size would take a long time to do, whereas I'm going to argue that you could put particles in the stratosphere very quickly. And so I think the space-based options won't really work as an emergency response system. To give you an idea of how fast you need to build these things, so we said each doubling of CO2 in the atmosphere traps 2 times 10 to the 15th watts. If we say this doubling is occurring on the century time scale, then that means that the radiative forcing from the CO2 is increasing at 2 times 10 to the 13th watts per year, which is about twice or somewhat more than the total energy consumption by mankind. And so the rate at which this radiative forcing is increasing is 600 kilowatts per second. And so if you wanted to match this with geoengineering, you need to block another 600 kilowatts of incoming energy every second. And I won't go through dragging you through all the calculation of the numbers of it, but if you wanted to do this with a space-based option, you'd need to build 54 square kilometers of satellite a day, which is more than a square kilometer every half hour, and that's just such a Herculean undertaking that I would say it's just easier to transform our energy system, and so I think the space-based options are interesting to think about, but not really practical from either an emergency response system, or even if you just want to avoid, it doesn't seem an attractive alternative to avoiding CO2 emissions. On the other hand, you'd think, okay, because the stratospheric system is working on the whole surface area of the Earth, you need 4 times as much area because it's not just the disk area. And so, well, if we needed 54 square kilometers for the disk one, we're going to need over 200 square kilometers a day or for this system, and isn't that worse? And the answer is that it's not really worse, and small, let's just do the spherical area, that if you want to get particles with an area of 8 million square kilometers, and you make them out of 0.1 micron particles, which happen to be the best size particle for this process, that 0.1 micron particles that would have an area of 8 million square kilometers would be a cube only 100 square meters on a side. So basically, if you could take a cube of 100 meters by 100 meters by 100 meters, grind it into 0.1 micron particles and loft it into the stratosphere, that would be the right amount of material. Now, I'm oversimplifying because the radiative properties of particles don't follow simple geometry, but just this is the right order of magnitude. And this is less than the amount of material that Mount Pinatubo, which was a volcano in 1991, put up in the stratosphere. And we could basically do the same kind of thing and put a cubes, 100 meter on a side cubes worth of material into the stratosphere, and that would be more or less enough to compensate on a global mean basis for a doubling of atmospheric CO2. Oh, I meant to update this slide. This should be more like 30 years for 50% in the atmosphere. There's a time issue here, in that if you drive a car home today, that about a quarter of the CO2 that comes out of your tailpipe today will still be in the atmosphere 1,000 years from now. And so if you expect to reverse the effects of CO2 release by geoengineering it, you have to set up some kind of institution that will last a mighty long time and be able to compensate for future emissions. So to compensate for 1 ton of CO2, which each ton of CO2 released blocks around 600 watts additional radiation from escaping to space. And so you'd need sort of an equivalent of disk area to block 0.6 of a square meter. And then say 30 years later, this should be updated, about half of it would be in the atmosphere. Maybe 50 years later, half of it would be in the atmosphere. You'd still have to block roughly 1/3 of a square meter. In 1,000 years, this, a 1/6 of a square meter or so. And so anyway, so there's a long time commitment to CO2, and geoengineering systems don't have intrinsically that same long time commitment. So I'm not, I'm more of a climate scientist than an engineer, but there was a 1992 National Academy study that looked at different ways that you could place particles in the stratosphere. And, the quickest thing seems to be taking a jet airplane up and releasing particles out the back of it. Or the other thing is to use high sulfur fuels, and there's various airplane-based systems that could be deployed pretty much right away. There are other ideas, like a balloon-supported smokestack to the stratosphere, or a hose, essentially, that the Department of Defense looked at. And the thing is that all of these things look like they would cost in the low billions of dollars, where the cost of energy system transformation is thought to be in the high hundreds of billions of dollars. And so economists who look at this in a purely economic way and believe these systems will work, that the cost, that it looks a lot cheaper just to try to geoengineer the planet than to reduce carbon dioxide emissions. Of course, it's far riskier. So one of the basic things of geoengineering is that if you look at the radiative forcing, or the heat trapped by adding CO2 to the atmosphere from a doubling of CO2, this is seasoned by latitude. So this is the South Pole, the North Pole. And that you see it's more or less 3 to 5, about 4 watts per square meter over the whole Earth. And it's relatively uniform, both seasonally and latitudinally. Whereas if we look at, and then if we were to turn down the sun by an equivalent amount, we would see that, well, the sunlight is mostly at the equator. It's mostly at the high latitude summers. And so that a reduction in sunlight looks nothing like the pattern from CO2 forcing. And so why would you, if you trap this much heat and then reduce this much sunlight with these different patterns, wouldn't you expect to have different residual regional climate change? And this is actually what, when I started doing this work, I thought it would never work, because I'd say, well, how could the climate effects of this change counteract the climate effects of that change? And we did a number of simulations. Here's more recent versions of them. And so this is a 2-time CO2 simulation using the NCAR community atmosphere model. And here's with a 1.8% reduction in sunlight. It needs a little more because of some feedbacks. And you can see that over most of the planet, it does a really excellent job. And if you look at this seasonally, it's doing a pretty good job seasonally also. If you do a standard thing that meteorologists do is you look at 30-year time series as to establish climatology, and then you can test statistical significance of changes against the natural variability of climate. And so here's for the double CO2 case, basically the temperature change is statistically significant everywhere. For just this 1.8% reduction in solar intensity, there's still some residual statistically significant climate change over 12% of the Earth's area at the 5% level. So you'd expect 5% of the Earth to be statistically significant just by chance. Now, this is an untuned system. If you go back to this other slide, you can see there's still a little bit of warming at the poles. And you can imagine a system that would put in more aerosols around the poles. And so if the most crude thing does this good a job, you would think, well, something a little more sophisticated would do a better job. And then if we look at precipitation, the statistically significant precipitation, that basically what you get in a global warming situation is more net evaporation around the equator, and then more water vapor transport to the high latitudes and more precipitation at high latitudes is a common feature of climate model simulations. And basically, what we found with the geoengineering is that in this sort of idealized geoengineering, that precipitation changes are only statistically significant over 4% of the Earth's area. You'd expect it to be over 5% just by chance. So basically, it's saying it's doing, within the detectability of this test, a perfect job. Now, this is a point-wise statistical significance. It turns out there actually is less precipitation in this case overall, but that would be statistically significant if you average over, say, all the land area of the Earth. But there's enough climate variability at any given point that it's not statistically significant at any given location. And so it seems to do a pretty good job both at reversing changes in temperature and the hydrological cycle. And this is pretty, with a very crude approach. It's basically just blocking sunlight top of atmosphere. So, the first objection, we published these kind of results, and people said, oh, but won't this hurt the biosphere because you're reducing sunlight and plants need sunlight for photosynthesis? And, the one observation, first of all, is that after Mount Pinatubo, by looking at carbon isotopes, you can tell whether carbon is going into the ocean or the land surface, and also by looking at oxygen-nitrogen ratios. And basically, the rate of CO2 increase decreased after Mount Pinatubo. And after some investigation, it was concluded that forests actually grew better, even though there was a couple of % reduction in sunlight. And that's because while there was maybe something like a 2% reduction in overall sunlight, there was something like, I forget the exact numbers, but maybe something upwards of up to 20% of the sunlight was converted into diffuse radiation. The diffuse radiation is able to penetrate deeper into forest canopies, and it looks like that photosynthesis in forests actually went up, even though overall sunlight was reduced, because the lower leaves were better lit and able to grow more vigorously. And so at least the observations after Mount Pinatubo is the biosphere grew more vigorously. In our simulations, also, the biosphere grew more vigorously in a geoengineered world, in the sense that the plants are constantly trying to get enough CO2 for photosynthesis, and they're controlling their stomatal aperture, so basically pores on their leaves, in order to get that CO2 in. When they open up their pores or the stomates to get the CO2 in, they lose water. And so by having more CO2 in the atmosphere, the plants can keep their stomates closed, and so they lose less water, and so they use water more efficiently. And this leads to eventually the biosphere supporting more productivity. And at least in our simulations, this effect, the effect of sunlight on photosynthesis is basically linear, so that it's sort of a 2% reduction in sunlight is more or less a 2% reduction in photosynthesis. And so in this simulation, at least, the CO2 water use efficiency effect was much stronger than the reduction in photosynthesis due to the reduced sunlight. And the result was that the biosphere, at least in the simulation, was much more vigorous. Now, what that means for the real world. Now, I have to say that some of my colleagues have gone around touting these kind of results as saying, oh, this is encouraging, and it says that somehow the geoengineered world will be better than even the natural world. And I think this is a misguided view, because especially for natural ecosystems, that even something that makes a natural ecosystem grow more vigorously is a perturbation to that natural ecosystem. It's not necessarily good for the ecosystem. We see putting more coastal eutrophication, putting more fertilizers in coastal waters is not good for coastal ecosystems. It's disruptive, and in the same way, this could be disruptive to ecosystems. So, one of the questions is, if we were confronted by a climate emergency, and I'll leave it up to you to define what that might be, how long would it take for a geoengineering scheme? I didn't make the whole sentence there. How long would it take for a geoengineering scheme to become effective? And we did some simulations last year, published in the Proceedings of the National Academy of Sciences, where we basically turned on geoengineering schemes. So we had this background red curve, which was a global warming simulation, one of the IPCC scenarios. And then, at different years, kind of turning on geoengineering to try to reverse this. And as you can see, that the temperature effects are seen in the subsequent year, or almost immediately. And the same is true of Mount Pinatubo. The next year was cooler, and that it continues cooling very dramatically for a decade or two, and then you have slower cooling after that. And so, and in contrast, if you would say, well, what is the time scale for response to a reduction in CO2 emission? That that even if we eliminated emissions entirely tomorrow, that would be enough to stabilize temperatures but not reduce temperatures, and that the full climate effect of a CO2 emission, or most of the climate effect of a CO2 emission, is not felt for several decades. And so, as I said, even if we went to zero emissions tomorrow, that would be just enough to stabilize temperature and not even reduce temperature. And so if we were confronted with some kind of catastrophic situation, that really emissions reduction is not even an option for reducing temperatures in the short term, but these geoengineering schemes are. This is sort of the flip side of that, is that if you had a geoengineering scheme and you were keeping your Earth cool, and then the system should fail at some point, you'd get the opposite thing, that you'd get a huge amount of warming right away. And so, and this could fail either for technical reasons or political reasons, or there could be a war or something. And so if you were masking huge amounts of warming by doing these geoengineering options and they failed, you could get rates of warming that were, say, 20 times faster than what otherwise would have occurred. The other point here on this figure is that we really don't know how much the Earth will warm due to a doubling of CO2. That there's an uncertainty in climate sensitivity. And if you continue geoengineering the planet, you might never actually find out what climate sensitivity is. And so the dashed lines are a case where the Earth is very sensitive to increasing CO2 content. The solid lines are where it's less sensitive. And so in the geoengineered case, you're both on those purple lines at the bottom, basically, you're down here and you're masking climate change. And if you stop the system, if climate sensitivity was high, you'd sort of rebound up towards that dashed line. If it's lower, you'd rebound towards that line. And so anyway, geoengineering might prevent us from learning how much climate change we're masking. So, geoengineering the whole Earth is a little scary. And so some people have said, well, could we do things at a regional scale? And so we started looking at the idea of, since the Arctic seems to be the ecosystem that's disappearing the fastest, with sea ice being lost and the southern end of Greenland possibly collapsing and so on, and the tundra melting and releasing additional carbon to the atmosphere, the question is, well, could we at least do something to prevent that and while avoiding some kind of global scale action? And this actually comes into the issue of what is a climate emergency. That, for example, Tom Wigley from the National Center of Atmospheric Research is basically, after some testing, more or less ready now to start geoengineering the Arctic, because he feels like we're already in what he would consider to be a climate emergency, in the sense that looks like we're losing a major ecosystem or biome type in the world, and also risking the loss of Greenland. And that, to him, is enough risk to want to start thinking about seriously deploying these kind of schemes. So we did some simulations where we just removed, what is this, 0.37% of the incoming solar insolation, and we just took a nick out of the sunlight coming in at the highest latitude areas. And then say, okay, well, what would this do to climate? So what if we just put, and the 61 degrees extends over Alaska, 71 degrees extends basically over the Arctic Ocean. And so this one would say, let's block 25% of the sunlight over the Arctic Ocean. And then this one would say, let's block 10% of the sunlight going down to a latitude that would include Alaska and parts of Norway and Sweden, Scandinavia, and Russia, northern Russia, and so on. And so this one, right? So one's taking 10% out north of 61 degrees. One's taking 25% out north of 71 degrees. So this is the same figure you saw before of the doubled CO2 warming. And then this is the effect of taking a quarter of the radiation out north of 71 degrees. And so this is basically just over the Arctic Ocean. And what you see is actually it's a bit of an overkill, that it's actually cooling now over the Arctic. So you'd probably want to do more like 21% or something like this. And you can see that the cooling effect extends down into the continents of the northern hemisphere. So you get some cooling further south. And okay, let's just do that. And so then if we do the 10% north of 61 degrees, and so 61 degrees is more or less, basically the southern end of Alaska. So you're getting, this one's going over where people are living, and so it would be more controversial. I guess both of them would be incredibly controversial. But again, here you see that for removing 10% of the radiation north of 61 degrees, you get significant cooling over, all of the northern hemisphere continents. And if we look at sea ice extent, well, I should show a more recent map, because this year I think last year sea ice was at an all-time minimum. But basically the Arctic sea ice is getting lost faster than anybody anticipated. Also, there's some indications that the southern end of Greenland may be beginning to collapse. That's somewhat controversial. And so we looked at the sea ice in these simulations, and say, could we get the sea ice to recover? And here's the control case, the sort of natural state. Here's the 2 times CO2, where you basically, in this simulation, just have a little patch of pretty dense sea ice, and then a lot of sort of not discontinuous sea ice. And basically, both of these 2 geoengineering cases sort of create a little bit too much sea ice. And we did a bunch of other simulations, and more or less, it's within our technological capability to make however much sea ice we want. So here's for the Arctic, the temperature changes that we predicted using, what our model predicted. And so here's the warming over the Arctic for this model, which is, again, the National Center for Atmospheric Research model. For the Arctic, for a doubling of CO2. And so we sort of overdid it a little bit with this 25% north of 71 degrees, and underdid it a little with the 10% north of 61 degrees. But basically, you could see that by turning the knobs, you could get the Arctic to be 0 temperature change. An interesting thing is that you don't do very much to reduce Arctic precipitation. And that's because, remember when we geoengineered the whole world, precipitation reduced a little bit, or somewhat, that basically at a point-by-point basis, there was no statistical change in precipitation. When we do the Arctic only, there's still lots more precipitation in the Arctic. And that's because the high-latitude precipitation is driven by evaporation in lower latitudes, and then that water vapor transport to the high latitudes. And by geoengineering the Arctic, you're not doing anything to reduce the evaporation in equatorial regions. And so the result is that you get much more snow because now you've cooled things off, but you're getting more or less the same amount of precipitation. And so you've got a much snowier Arctic. And so some people would say, oh, okay, well, this is imperfect climate modification. And now other people like Mike McCracken have said, well, maybe this is what you want to do, because if you're worried about Greenland collapsing, what you want to do is put as much snow on top of Greenland as possible. And so geoengineering the Arctic would do it. Another thing that's been raised is this issue of, well, won't this destroy the ozone layer if you put a bunch of particles in the stratosphere? And certainly this needs more attention. But the first thing we can see is what happened after Mount Pinatubo. And so this is 1991, Mount Pinatubo going off. Now, just so you see the scale here, this is a measure of the amount of ozone in the atmosphere. And so this is 280 Dobson units, 290, 300. And so the estimates are that there was something like a 3% reduction in total ozone after Mount Pinatubo. But it's hard to say what's due to shifts in, the particles from Mount Pinatubo only stayed there for a year or two, and there's problems of intercalibrating units, different satellites and so on. But basically, while there might be a couple of % reduction in stratospheric ozone, that it wasn't a major effect. Furthermore, the destruction of the ozone depends on having chlorine in the stratosphere from CFCs. And because of the Montreal protocols and the reduction in CFC use, the chlorine in the stratosphere is decreasing. And by mid-century, it's thought that there'll be so little chlorine in the stratosphere that even if we threw a bunch of particles in, it would have virtually no detectable effect on ozone. And so again, well, this is a research issue. There's no evidence that there would be any major destruction of the ozone layer or anything like that. But these are all preliminary results. So what are some of the concerns? And that I think well, one is the ozone layer, which obviously if it destroyed the ozone layer, that would be a bad thing. But there's another kind of thing that many people, including myself, are worried about, and that is just that the perception that there's a technical fix could reduce pressure to reduce CO2 emissions, and that if say these preliminary simulations indicate, well, while there are some problems, that these schemes would basically work, that it's a rational. If the existence of these schemes reduces downside risk, a rational response is to engage in riskier behavior, right? So if flood insurance is available, it can become rational to build a house in a floodplain, whereas if you didn't have flood insurance, that might be irrational behavior. And so insofar as there is some kind of potential for insurance against some kind of climate catastrophe, that this could, the logical response is to work less hard to reduce CO2 emissions. And so this is a danger. And the other thing is just this unintended environmental surprises, in that nobody predicted the ozone hole from CFC emissions. Nobody predicted that lead in gasoline would damage children's brains. And nobody predicted that the MTBE put in our gasoline would pollute our groundwater. And so, and if you look at the history of, in Australia, where they would introduce, cane toads to eat something else that was eating something else, our history of interventions in natural systems is one of, where the system responds in some unanticipated way. And so, you could be sure that whatever we have in our models, if you actually did this, something would happen that's not represented in the models. And so, anyway, it would counsel in favor of a cautious approach. I guess there's one other thing I want to bring up, and that's the whole issue of ocean acidification. My postdoc Long Cao here and myself have been doing some work on the effects of carbon dioxide on the marine environment. And if you see these dots over here represent the location of coral reefs. This represents 280 ppm as the concentration of CO2 in the atmosphere before the Industrial Revolution. And you can see most of the corals are in this blue zone where aragonite saturation is greater than 4. This is a measure of the chemical potential of the ocean that's helping to drive coral skeletal development. And then there are a few corals in these sort of green colors, like you hear off the coast of Australia, or anyway, in a few places you get some corals in the greens. But basically, by the time you're in the yellows, there's no corals that are able to live sustainably in those kind of environments. And so if we see how this is marching into the future, that that things look pretty dismal, that even by the time, say, you're at 560 ppm, which is a doubling of CO2, you've basically lost all the water in the ocean with the kind of chemistry where corals have been found living sustainably. And so I think there's at least an expectation that, or if not an expectation, anyway, I would say for me it's an expectation that at a sort of doubling of CO2 that coral reefs will no longer be able to sustain themselves in the ocean. That's not to say that they'll die off right away, but it's a question of ecological competition that, if aragonite saturation is somewhere down here, say these orange colors, that a coral might be able to survive, but if there was a hurricane or some kind of disturbance, and then it comes time to repopulate that area, it's likely that seagrasses or algae or something else will occupy that space. I guess the other thing I want to say is this purple color, the shells of some marine organisms will actually start dissolving in these areas, and there are marine organisms that live in the ocean that make their shells out of this mineral of calcium carbonate, and by the end of this century, or even around mid-century, with here it's only 400 something ppm before some shells start dissolving in the ocean. And so, that basically, unless we reduce CO2 emissions very soon, major components of our marine ecosystems will be gone. And I don't need to go into these issues, but so the point is that while these geoengineerings might be able to undo some of the negative effects of climate change, there are chemical effects of CO2 that they will do nothing about, and those in themselves, I think, are sufficient reason to reduce CO2 emissions. So I guess what I want to say here is that this whole area is in its infancy. There's basically been almost zero money, and it's starting to change a little bit, but say up until last year, not a single dollar of federal research money had ever been applied to geoengineering research. Not that the Bush administration is ideologically opposed to these kind of things, but I think it's just so politically a hot potato that they didn't want to touch it. That the preliminary results indicate that a high CO2 world with geoengineering may be more similar to the pre-industrial world than would be a high CO2 world without geoengineering. So it's not saying that a geoengineered world is somehow better than the natural world, but it's not. It seems hard to argue that a high CO2 world with lots of climate change is better than a high CO2 world without lots of climate change. I guess the other conclusion here is that that geoengineering is something that could be deployed rapidly in response to a climate emergency, whereas the emission reduction approaches would take much longer. And but the sort of caveat in all this is that the Earth system is notoriously complex, and one can assume that tinkering with it on a global scale will produce unanticipated outcomes, which is pretty scary because if we do any irreversible damage, there's not much you can do about it. So, but I don't think it's a simple thing, and especially say with this Arctic case, that's supposed to tug at your heartstrings. That that is it. Which is the really more environmentally and green, environmentally conscious thing to do? Is it better just to let Arctic ecosystems disappear, and the biota that lives in those ecosystems, or is it better to put some particles in the stratosphere over the Arctic? And I don't think it's obvious which is the more environmentally sensitive thing to do. Is it environmentally sensitive just to let Arctic ecosystems disappear? And obviously it's best to get rid of CO2 emissions, but as my earliest slide showed, we don't seem to be doing that yet. And this, I think, actually a slide I stole from Marty Hoffman and changed it a little bit, but that it seems to me that we, that we need, that basically we need to, if we assume that we want the world to develop, and we in the industrialized world can say, oh, well, we don't need to develop more, but certainly if you're in Africa or many other places, development seems like an obviously good thing. But we can either develop in ways, let's say, by putting out lots of coal-fired power plants and then trying to geoengineer our damages around this, or we can develop approaches for growth and development while diminishing environmental risk. And my little, I know you guys are investing in high-altitude wind power. There are different designs, but I really think that the ultimate thing we need to develop are new energy systems that can fuel growth and development and our industrialized world without damaging the environment. But it seems that we're getting there way too slowly, and that we really need to start thinking about our insurance policies of what will we do if things really go awry. So I think I'll just close it there. So that's it. Any questions? Could you use the mic over there? It would be the best thing.
Yeah. I guess it strikes me as a little, I'm not sure what word I'm blocked on. Let me phrase it differently. You talked about how we should be doing controlled and thoughtful development of our energy resources, because the alternative, which is unplanned growth and has all this risk, is probably bad and nefarious, and I agree with that. And if that slide were your only slide, that would probably be great. But you just went through this whole presentation. At the end of it, you said, basically, we have no idea what the consequences of this kind of meddling in the Earth's ecosystem would produce. And furthermore, what you didn't say was that these climate models are not even necessarily accurate representations of the Earth's system. So, yeah, all that's true, but I don't see that you've proven or even suggested that geoengineering is even a sane thing to do without some sort of science behind it. You could build a simulation of anything and say, look at these graphs it produces.
Yeah. What can I say? I can say that these climate models are the same climate models that are used to predict what might happen from continued CO2 emission. And it's known that these models are deficient. And that's why we don't know how much warming there'll be. And you also, and I think I said several times that we would anticipate that it wouldn't work the way the models say, that there would be surprises. But now some of these simulations have been done in a number of different models, and also there are some basic physics reasons why it seems it works. And one of the main things is that it turns out that sea ice is a really important component in the climate system, in that if you have sea ice in the winter in high latitudes, that insulates the atmosphere from the ocean and allows the atmosphere to get very cold. And if you melt the sea ice, then in the summertime, all kinds of heat can run into the ocean, and in the wintertime, the heat can run out of the ocean. And it seems that, and those heat fluxes associated with having sea ice or not having sea ice can be on the order of 100 watts per square meter, whereas the radiative forcing from CO2 doubling is, say, 4 watts per meter squared. And so if you get the sea ice back to where it is, then you get these sort of 100 watt per square meter fluxes back to where they were before, and the climate gets closer to its base state. Now, I don't think, the reason, I think people who've been talking about this would say, okay, in the polar winter, the air mixes vertically in this winter time, and so if you threw some particles in the spring, they would presumably get rained out in the next winter. Now, I'm not advocating doing this, but the people who are advocating doing it, who would say, okay, you would start, with this kind of phase thing, then see what happens. If nothing bad happens, then try it for 2 years, 3 years. If it works good, you extend it. So I think even the people who think it's ready to deploy these kind of things would see some kind of phased and gradual phase, and so there'd be some feedback, so you see if something bad is happening. Myself, I think if you tried anything like this, where there's something short of mass famine in the developed world, that you would have so many protesters in the street and people would lose elections. That I think a politician who said, "Oh, let's spray particles in the stratosphere," I don't think that's going to win them elections. So, I think that it would not. My guess is it won't get deployed unless there's real starvation in the developed world. Okay, but I think by then the danger is that a politician will go and do something crazy, like maybe he'll put this. There'll be such political demand to do something that they'll start spraying sulfate particles all over the place, and then maybe something really disastrous would happen. And so I think it's worth doing the research up front to have some idea of what might happen. But I don't think it would get deployed in a practical sense outside of something pretty clearly catastrophic going on. But that's just my own personal view. Yes?
I was just wondering, given the examples you were showing of having the sort of targeted aerosol, like over just the Arctic cap, et cetera, how would you keep the particles isolated once they're up in the stratosphere? I'm just wondering.
This was idealized. They wouldn't really stay that. In fact, Phil Roche has recently done a simulation with particles and they would, basically, the general stratospheric circulation is, upwelling at the equators and downwelling at the poles. And so to a first approximation, if you put something in at some latitude, it would tend to go north and go down. But it doesn't, there's sort of quasi-diffusion, and it wouldn't really be as neat as this, is the answer. Anything else? Okay, so maybe we'll hold it there. Thank you for your attendance.